Welcome to the Lesson BC YouTube channel. Today, we're diving into electrical power. And hey, if you find this helpful, don't forget to like and subscribe to our channel. So think about it. From the tiny charger that powers your phone to the massive lines that power our cities, they all run on the same fundamental principle, electrical power. But what is it really? And how do we actually calculate it? Well, in the next few minutes, we're going to break it all down.
All right, here's our game plan for this explainer. First, we'll get a handle on what electrical power even is. Then we'll jump into the core formulas you'll be using all the time. After that, we'll see how it all works in the real world, clear up that classic confusion between power and energy, and finally, we'll put everything together in your very own power toolkit.
First up, what exactly is electrical power? Before we start throwing around formulas and numbers, we need a really solid idea of what we're talking about. And as you're about to see, it really all comes down to speed.
At its very heart, power isn't about how much energy there is in total. Nope. It's all about how fast that energy is being used or moved from one place to another. You can think of it like the flow rate of energy in a system.
In the fundamental formula, it's beautifully simple. Power equals work, which is really just another word for energy, divided by time. The standard unit we use is the watt, which is literally just 1 joule of energy being transferred every single second.
Okay, so now that we have that basic definition down, let's see how it builds into the formulas that you're going to use most often when you're dealing with actual circuits. This is where the theory really gets practical.
But before we get to the equations, let's meet the key players in our story. You've got P for power in watts, V for voltage in volts, I for current in amperes, and R for resistance in ohms. You're going to be seeing these guys a lot.
This one right here is the big one. It's the foundational equation for power and electric circuits. All it tells us is that the power being used is just the product of the current flowing through something and the voltage across it. It's simple, it's elegant, and it is incredibly powerful.
Now, here's where things get really cool and versatile. This first formula, P equals IV, can actually transform when we team it up with its good friend, Ohm's law. By swapping in parts of Ohm's law, we can unlock 2 new ways to calculate power that are super useful.
So, what if you know the current and the resistance, but you have no idea what the voltage is? Well, this formula is your best friend. It's especially important for understanding how much power gets lost as heat in wires, because that heat loss is directly tied to the square of the current.
And on the flip side, if you know the voltage and the resistance, this is the one you'll grab. I mean, think about how amazing this is. You can figure out the power of any part of a circuit without even needing to measure the current that's flowing through it.
So that's enough theory for now. Let's make this all a bit more tangible. Let's look at some real-world examples and see these formulas actually do some work. So, think about a standard light bulb. The box says it's a 60-watt bulb, but what does that really mean? Is it always using exactly 60 watts? Well, since it's running on alternating current, the answer is not quite. Let's find out what's really happening.
And here's the solution. Because AC power pulses back and forth in a wave, the power isn't constant. In fact, it fluctuates, hitting a peak value that is exactly double the average power. So that means our little 60-watt bulb is actually pulsing between 0 and 120 watts, 120 times every single second. Our eyes can't see that flicker, of course, so we just see the average brightness.
Okay, now for a much bigger problem. This is a massive challenge for power companies. How do you get electricity hundreds of miles away from a power plant to your house without losing most of it as heat along the way?
So how do we tackle this? First, we use our P equals IV formula to figure out the current flowing through the line, which is a whopping 500 amps. Then, we plug that huge number into our heat loss formula, P equals I squared R. And just look at that result. Even with a tiny 1 ohm resistance, we lose 250,000 watts. That's a quarter of a megawatt of power that's just gone, wasted, radiated into the air as heat. And these principles scale up and down. It doesn't matter if we're analyzing a single tiny resistor, a simple series circuit like this one, or the incredibly complex network of circuits inside your smartphone. The exact same fundamental power calculations apply to every single component.
All right, this next point is a really common spot for confusion, but I promise the difference is actually very simple, and it's super important for understanding things like, your electricity bill.
Here is the absolute simplest way to think about it. Power is like your speed when you're driving. It's how fast you're going right now. Energy is the total distance you've traveled. It's how much ground you've covered in total. One is a rate, the other is a quantity.
And this formula comes straight from our very first definition. We've just rearranged the pieces.
It shows you perfectly that the total energy you use depends on two things: the power of your device, how fast it eats energy, and for how long you leave it running. This is exactly what your electricity company measures.
Okay, we have covered a lot of ground here, so let's wrap this all up by putting our key formulas in one convenient place for a quick review. This is your go-to reference sheet.
And here it is, your complete power toolkit. You've got the foundational definition of power, which is energy over time, and then you have the 3 workhorses for circuit analysis. Depending on what information you have about a circuit, one of these formulas will be the perfect tool for the job.
And to leave you with a final thought, we've seen that power loss is driven by P equals I squared R. That means it gets worse with the square of the current. So given everything we've just talked about, can you see why engineers go to the extreme and dangerous trouble of using incredibly high voltages to send power across the country? The answer is hiding right there in the math we just covered.